exercise sheet 7.1 about power series. This is the continuation. We have one more exercise left. It's number 4, and it's about power series and differential equations. This is quite an interesting specialty, although you haven't yet really talked about differential equations in the course, which will come later in the semester. You will know that something like what you see here, something like this is an equation which presents you an unknown function f of x. This is called an ordinary differential equation. By the way, my personal abbreviation is DEQ. Usually people abbreviate it with DE only, but I think DEQ is a little more less ambiguous, let's say. So please allow me to do so. Also, yes, minimize this here. It's better now. So this one is, as we say, it's second order. Why? Because the second derivative of the unknown function f of x is also inside this equation. There might also be the first derivative inside. This is not the case. But anyway, the highest derivative that appears in such an equation defines the order of such a differential equation. Also, it's homogeneous. That's quite the same way of speaking as with systems of linear equations, as you remember. If the right-hand side is 0, in this case, we call this a homogeneous differential equation. And last but not least, it's also linear. It's linear because the unknown function and its derivatives all appear directly without any power given, like squared or cubed, or even more complicated things like non-linear operations performed on these terms. So that sounds quite simple. Well, you could say it is, because this is probably one of the most famous ordinary differential equations that you encounter when dealing with this sort of question for the first time. If you have certain knowledge in classical physics, especially mechanics, you will know that it looks like sort of a so-called oscillator equation. That there's a strong connection to the second law of Newton, you know, that fundamental theorem of movement by classical mechanics. Anyway, you could say this term in the physical case, this term has something to do with the acceleration of such a moving object, and this is its position. And the statement of this equation, of course, is that the sum of sort of acceleration plus position in a certain sense is always equals 0. Usually there are some additional coefficients inside which describe the mechanical properties of that system. Now, mathematically speaking, this is just sort of a puzzle, you could say. Try and find a function which has this special property that its second derivative is basically speaking identical to the function itself, but important detail, it has the opposite sign. Okay, so if this is always opposite to this one, the sum of these two terms results to 0. That's what we want. But also make yourselves familiar with this sort of equation which holds a unknown function, so that x no more is anything like an unknown variable, but instead this equation must hold for any value of x. And there's no restriction given, so we should suppose that it's valid for any value of x, element r, and that's what we do. Now, the approach just in this exercise is just to try and use a power series. f of x is our unknown function, but we construct it by means of a infinite power series in the usual way, summation over n, starting from 0, approaching infinity, and using an as a coefficient, and then, of course, x to the power of n as our usual power term inside. And don't forget that the element number 0 is always a pure constant. These coefficients, of course, are unknown. It means that now we have, if you want, an infinity of newly created unknowns, but now comes the trick. What do we do? Well, first step, we just differentiate this function by approach without knowing what these coefficients exactly are. So f prime of x will be the summation also over n. And now what we use is very familiar to you. We take the exponent as a factor, and then we reduce it by 1. That's the usual way of differentiating power terms. Please note, the variable x must be in the basis, must be the basis, and the exponent must be constant for this rule to be used. Don't mix it up with any sort of exponential function, sort of like a to the power of x. So if x is in the exponent, you have a completely different sort of function and also different differentiation rule, of course. Now, what I'm doing here implicitly is I use term-by-term differentiation. So that's nothing special. We've done this before, but also important is to remove the 0 element since it's an additive constant, so it just disappears, and it's important to start counting from n equals 1. Now, you can test it, right? If you take your time and just test whether you can also explicitly write down the first few elements of this kind, and then see what happens if you differentiate them term by term, and you will agree that the numbering must start at 1 right now. So, but we also need the second derivative. This is a second order differential equation. The second derivative is much by the same method taken from here by differentiating this symbolic term again. So now the new exponent gets another factor. I sorted this in this way, n times n minus 1. So in a descending order. Then our original coefficient still stays there as a constant factor. Yes, it's not affected by the differentiation, of course. And the exponent is reduced one more time. And so we have x to the power of n minus 2 inside. Also, this time the first element, which is corresponding to n equals 1, is a pure constant, as you will know. After differentiating this, the n equals 1 element is the constant. So again, this disappears by differentiating, and it's important to start numbering from n equals 2 this time. You can also test this by hand. Now, we have, very important, we have two initial conditions. These are given basically for us to get along a little easier. We could also find the more general solution, but this would be plenty much more work for us to do. And it turns out, and this is just a question of experience probably, it turns out that using these initial conditions right now is a good idea, or let's say as early as possible. So what is demanded here? F of 0 should be 0, and f prime of 0 should be 1. You can imagine what this means graphically. The graph of our function, first of all, must contain the origin. That's what it says. That's all it does. It says that the function at x equals 0 is 0. So this is the origin contained in the graph of this function. Also, this means that the tangent at this position has a slope of 1. So we have a 45-degree slope by probably, let's suppose it's just a regular intersection point. So the graph of our function will intersect the origin at an angle of 45 degrees. That's all it says. And now let's use this algebraically. Initial one, just for short, f of 0. And now of course, I insert x equals 0 in my approach, which means that, and then allow me just to leave this summation notation away, because it's a little more easy to understand if I just write down the first few elements. So a0, of course, is a constant, plus a1 times x power 1. So that's the linear term. And I have 0 inserted for x, so a1 times 0 plus a2 times 0 squared, and so on. By the way, I decided to construct this power series at x equals 0. You remember this so-called expansion point that's in the general formula. You remember this x. I called it x0, but I found out it's usually denoted to be x null. So I will try and say x null from now on. So this so-called expansion point, which is constant, is set to 0 in this case, which is just the, well, you could say the simplest, but also the most convenient case. Now, what do we get? We find out that all these terms, except for the constant, go away. They get 0, they disappear. So what stays is that f of 0 equals a0. And in the end, it means that a0 equals 0, because this is the first initial. F of 0 should be 0. So that's already the determination of our first, or let's say our coefficient number 0. What does it mean? It means that the function that we're looking for will not have a pure constant in its power series, which is very clear because, as we all know, otherwise it would not be 0. It would not contain the origin. Its graph would not contain the origin. Second initial, f prime of 0, look here, should be 1. That's given. But also, this is our first derivative by approach, which says that we have to sum from n equals 1. Now you will see 1 times a1 times x power 0 means that the original linear coefficient is now the pure constant in the first derivative, this one. It also verifies that we've done everything right here. So plus the next is, you see here, 2 times 1, so just a factor of 2 times a2 times now x power 2 minus 2. Am I right? Sorry, I'm the wrong row here. I must go here. Sorry, that was a mistake. Here, n equals 2, then I have 2 times a2 times x power 1. So that's the linear term, actually. But x is equal to 0 again. Let's look at the next, the third term also, n equals 3. So we have 3 times a3 times x power 2 this time. But anyway, I get 0 squared. It's the same effect as before. All these terms disappear except for the constant, but it's the original linear coefficient this time, which remains. But it's not also, secondly, it's not to be set equal to 0. Instead, it has to be equal to 1. So that's all we can extract from these initial conditions. A0 must be 0 and A1 must be 1. That's it. Now inserting our approach into the differential equation gets interesting, because we can, I use the same method again, so it's a little easier to understand if I go away from this, if I leave away this summation notation, okay? So let's see here, n equals 2. So that's, you could say, the starting element of this second derivative. It's 2 times 1 times a2 times x, what do we have? Power 0. So this time, 2 times a2 is the pure constant in the second derivative by approach. Plus, now comes the linear term. The linear term corresponds to n equals 3 in this notation. 3 times 2, you know, always a number times its predecessor, times a3 times x power 1, because 3 minus 2 is the exponent. So that's the linear term, actually. Oh, I'm here. Okay, right? Times x. This time x is free again. We have already used our initial conditions. Now we are very general. And well, it's not so surprising what happens next. It's just always the next natural number times its predecessor times the next coefficient, and so on. And the exponent rises, x squared, x cubed, and so on. Now, the function itself, look back here, is this one. So we can just add it term by term also, and then just place our elements where they fit best. You will see what I mean soon. I start with a0, the constant, plus the linear term, plus now this is nothing special. The quadratic term, of course, the cubic term, and so on. Now, what do we see? We see that since the sum of these two parenthesed expressions must always be 0, it's the so-called zero function. Please remember, this means that it's 0 for any value of x. Can only mean, or you could also say it enforces all these coefficients to be adjusted in a certain way so that this whole expression disappears for any value of x, which leads us to a so-called very famous method called equating coefficients. This is like a little bit like Germanism. I translated the German expression Koeffizientenvergleich. In English, it would be coefficient comparison. But the official expression, as I found out meanwhile, is equating coefficients. But you will probably know what I mean. I hope so. It means that for any power of x, the coefficient on both sides of the equation must be the same. Okay, in the end, and now in this special case, we have a 0 on the right side. This 0 means that all the coefficients on this side are 0. And so in the end, if I just sort this by powers of x, also all the resulting coefficients must exactly be 0, much the same. So every single combined coefficient of this new power series must be 0, so that the 0 function results. That's what we have. Let's see. Since we already now know, and that's really an advantage now, that a0 equals 0 and a1 equals 1, we can use this right away. Otherwise, it would get much more complicated. Okay, so you follow me because I abbreviate a little bit. I would say this is the total constant on the left side of the equation. The only two expressions which do not contain x. So since here's a 0, a full 0, it means this in sum must be 0 also. Since a0 is already 0, a2 must be 0 too. Okay, so this is 0, so that this contribution must be 0. 2 times 1 times a2 equals 0 means a2 equals 0. That's it. The next one, you can sort of pull this factor of x outside of parentheses, put these two elements in parentheses, then you would have 3 times 2, of course, is 6. So like 6 times a3 plus a1 equals 1. Now, I carefully put these factors here in a way that you see where they come from. I did not combine them to be 6, 12, 20 or something, because it's quite obvious that this has something to do with factorials, what we see here, okay? So just look here. 3 times 2 times a3 plus a1 equals 1. Is that true? Yeah, it is, but how do I get my... Ah, yes, right. And then I should make a little note here for a moment. If I have like 3 times 2 times a3 times, and not times, but plus a1, you know what I mean, times x. This is pulling x outside of these parentheses, or putting the coefficients in parentheses of this linear term. So that's what I have. And this whole factor must be equal to 1. But I'm just having a little problem right now. I don't know what's going wrong. Let me pause just for a second. So that was a little mistake just by myself. Very silly mistake. Of course, A1 equals 1. But as I said before, all the coefficients of this series must be 0. So it means replacing this A1 by 1, the whole coefficient must be 0. And now we can immediately see if we just isolate A3. A3 is then, if I pull this 1 to the other side, it gets -1. I get -1 and then divided by 3 times 2. And as you see, I can complete this if I want with a factor of 1. So it's obviously the factorial of the number 3. So that's negative reciprocal of 3 factorial. And that looks very familiar if you remember, or if you already know the Taylor theorem, the famous Taylor theorem, which also contains these factorials in the denominator by, you could say, by theory. So anyway, roughly speaking, we know where all this comes from. Now, the next step is interesting because obviously the fact that A2 equals 0 has just transferred to the conclusion that A2 must also be 0. So this one is 0, and then also this gets 0. And now in the next step, looking here, the same effect again. Since A2 equals 0, so all that remains is 4 times 3 times A4, having to be 0 for the same reason as before, because we have the 0 function. All the coefficients altogether of this combined power series must be 0. It means that immediately also A4 gets 0. The same effect happens with any even coefficient. Okay, so all these, like A6, A8, and so on, they all get 0, which is an interesting effect. And next here, A5, that's the same. Again, we found out that A3 is this expression. We could insert it here, or let's do it this way. I can isolate A5 when I say this combination of coefficients must be 0. I can isolate A5, and what I get is A5 must be equal to negative A3 divided by 5 times 4. And now inserting A3, which is negative 1 over 3 factorial, I get 1 over 5 times 4 times 3 factorial. That's nice because this completes my factorial of 3 to a factorial of 5. And this time it has a positive sign. So that's quite nice. It's a nice pattern that arises. And this is already enough for you to do, to quite surely, to be quite sure, let's say, that this pattern has been detected and will go on much the same way. So that's why I write and so on, analogously. What have we found? We found that the unknown function f of x must be something like, you remember A1 equals 1, that was part of the initial condition. So our constant term, due to this first initial, disappears. The linear term is just plain x. The next is, looking here, negative x cubed over 3 factorial plus x power 5 over 5 factorial minus x power 7 over 7 factorial plus minus alternating sign and so on. So this is probably already familiar to you because it's one of the most famous so-called Taylor series, which belongs to our sine function, which is the most important harmonic function, periodic function, which is, as you also know, the standard solution of any harmonic oscillator equation in the case without damping. And that's what we have here. You could say this is the mathematical version of the differential equation of a harmonic oscillator without damping, so-called free oscillator. So that's no surprise having the sine as a solution. Cosine would also be fine but not as long as we have the initial conditions which are given. As you remember, the graph must contain the origin and it must have a slope of 1 there. And this is what the sine curve quite surely does. And also, after having used this explicit way, of course, it's a good idea to put this in a closed form by the summation notation. This should be, it's a good test for you to try this on your own. You just construct an alternating sign by saying -1 in parentheses power of n, and then you just check if whether that sign change is correctly represented. As you see, if n equals 0, or for any even n, I get a positive sign. Now, please don't overlook that every second term of the Taylor series has disappeared, like the constant, the quadratic, and so on. All the terms with even exponent, but that's already considered inside here, because I use x to the power of 2n plus 1. That's the usual way to construct an odd number, as you know. So actually what I'm doing here is I try using power 2n plus 1, then I test it and say if n equals 0, I have x power 1, so that's my linear term. The sign gets positive. The n value is still 0, okay, although the exponent is equal to 1 right now. So I get a positive sign, I get 1 factorial below, and that's just my linear term x. Let's test for n equals 3, just for fun. Then we have x power 2 times 3 plus 1 is 7, x power 7. We have -1 power 3, which is negative, and we have 7 factorial in the denominator. That's exactly this term with a negative sign. So everything's fine. And then just to complete it, the second part asks about what we've already understood, which well-known analytical function does this power series represent, and why is it so? We've talked about harmonic oscillator and things like that. You also know that the second derivative of sine is negative sine of x, so that's quite nice. You are asked to explain this by using standard knowledge from calculus, and this is what we've done. The differential, just to summarize, differential equation describes harmonic oscillator. F of x is the natural sine function. Natural means without any modification, okay, with properties as follows. First, f prime of x equals cosine x, that's what we know, and so the second derivative will be equal to negative sine of x, and that's exactly what we need, because this is the negative value of f of x itself. If we insert these both in the differential equation, they fulfill it for any value of x, so it fulfills the differential equation. Second graph contains the origin, it has a point symmetry to the origin, and third, it has a slope of 1 at this position. Thank you.